Well, good morning, everybody. How we do? Happy Monday? Yes, no? Yeah. A couple of things. Today is lecture, right? Because we've got more content in this unit than we normally would. Next Monday is lab. We'll do the actual optics labs where we'll do lenses on the tabletop and we'll get you into virtual and real images and all that sort of stuff. And then I think, aren't we like up against spring break at that point? I think spring break happens. And then you're coming back right after spring break and taking an exam. Like the Thursday we get back from spring break is our exam for this unit. So that's kind of the next 3 weeks. This week will be all chapter 26. So I'm starting 26 today, and then Tuesday and Thursday will continue to be into chapter 26. The goal for today is to learn about refraction and Snell's law. We're going to get into a couple of really cool tangents that have to do with refraction. And then starting tomorrow, we're going to start applying refraction to lenses. I think, let's see, believe that was all the things that I had to, oh no. I got an email this morning that the evaluations are up for you guys. Has anybody gotten an email? Student email for the evaluations again. So my plea to you is to please go and do that. It's my favorite part of the evaluation process. It really is. I love reading your comments and things like that. I mean, at the bare minimum, fill out the bubbles, but if you could, just leave me some real honest feedback. I can never see who's writing what. I don't know who it is, so you can say whatever you like there. If you leave an inside joke, then I'll know who it is. But go ahead and do that for me. I really, really appreciate it. Speaking of evaluations, Dean Shirley McManus is with us here today. She's right here. She'll be evaluating me along some other lines. You really shouldn't do these kinds of things at evaluations, but we're going to do two things right away. Number one, my first piece of evaluation I ever got from Dean McManus was 24 years ago, 24 and a semester ago. Okay, it was informal, so she wasn't officially visiting my classroom. She just happened to stop by my very first week of teaching. And after I was done, she pulled me outside the classroom and she said, "Look, you look too much like a student. I need you to go get some teaching clothes." Do you have any memory of this?
Oh, yeah.
Yeah. Because I was wearing jeans and a t-shirt, teaching my classes. She's like, "You're too young. You look too much like the students. Go get some teaching clothes." From that time on, I've worn slacks and a t-shirt for every slacks and a button shirt for every lecture. And this for every lab. So you can thank her for that. She hired me. She was on the hiring committee that hired me, right? Yeah, so you guys know where to go, right? When the homework's hard or the exams are too hard, it's her fault. But I want to I'm going to give you the next 2 to 5 minutes, okay? It's not often that students interact with a dean. Usually you're in trouble if you're interacting with a dean or something's gone wrong. I just want to give you the next 2 to 5 minutes to ask whatever question you like of Dean McManus, right? Anything you're curious about, campus, the division, me, doesn't matter. You are allowed to ask her. Go. Yeah, they're free. It's okay. They'll warm up. They'll figure something else out. But this is your chance, right? No threat from the dean, nothing.
I don't even know who you are, so it's safe.
Yeah, and I won't tell her.
Been here 34 years. Probably older than some of your parents.
Questions about scheduling? Nothing? Wow.
We would have maybe known about this a little more. Probably could have prepared some questions.
Right? I could have told you ahead of time. Yeah, honestly, I couldn't remember which lab she was coming to today, so that's part of the reason I didn't tell you. Thank you. Honestly, this was the class that I said you were coming, was this like 2 or 3 weeks ago? And we almost hatched a plan to wear costumes. right? We were going to wear hats or something, right? So that when you came in, we were
We
all...
used to wear Hawaiian shirts and refresh.
Right, something like that.
All the faculty. I don't know. I think it was COVID.
Yeah, COVID really kind of threw... We came back from COVID and everybody was wearing masks, and we used to do some pretty good practical jokes around here. And the political climate of the school had shifted a little bit post-COVID. So it was kind of frowned upon to have fun at work anymore. So. But that doesn't stop me. It doesn't stop me. Well, if you ever have questions about what's going on around you, please, her door is open, right? And you can go see her before you get in trouble, right? And just stop by the division office. It's right at the base of the stairs. And even if you want just stories or ammunition against me, she can provide. All right, we are going to do a demonstration first, okay? I have set up the 2 mirrors that I brought into class in the lecture room that not everybody could see. And so what I want you to do, got a spot over here, got a spot over here. You're going to take turns. What you need to do, the convex one is not going to change very much, but it's the concave one that's going to mess with your brain, right? I want you to walk up to it, and I want you to kind of experience the difference between a real image and a virtual image. You're going to stand in front of it and you're going to walk towards it, okay? It's going to start off inverted and real, and then it's going to flip to upright and virtual. And when you do that, you might have to get down kind of close to it to be able to see it, okay? But I want everybody to come up and kind of have that experience right now so that when we're talking about real and virtual, you have a feeling for what it's like. So groups here, just kind of line up and give everybody a shot to do it. Go. Well, you were on the front row, weren't you? Yeah, so you saw it already.
You just wanted to make sure it was not true.
Right. That I've changed it.
It's trippy.
So do you feel changed now? Have you seen the innermost parts of your soul in doing this? Okay, Alex, way too much fun. Way too much fun. So that had everything to do, right, with our law of reflection, what we were talking about last week. We did 2 of those chapters last week about the law of reflection and then about mirrors. So today, like I said, we're going to lay the groundwork for being able to do lenses starting tomorrow. But before we get there, we have to talk about the law of refraction. Let's see, we always have, right, some sort of surface, some interface where the light's coming in. I didn't draw that one very well. Where do we measure our angles from in optics? The vertical, right? We call that the normal line. So let's see, we're going to have some, we'll do light coming in like this, right? And we know that on most surfaces, we're going to get some kind of reflection, right? The light's going to bounce off. Does anybody remember the rule? What's the angle on reflection? Angle in equals? Yeah, good. There you go. Okay. I'm gonna fall back on some of my notation that I learned in optics. You notice there I wrote theta 1 with an apostrophe on it. We call that theta 1 prime. It's just going to start clearing up a little bit of the confusion that we're going to run into with refraction. Okay, so we have that bounce. That bounce does happen. But today, we want to talk about what the light does when it enters the material. And it's going to bend. It's going to refract. It's going to change its direction that it's traveling because it passes into another medium. All right, former 2A students, I hammered this one into a lot. The speed of a wave depends on the, does anybody remember? Good, the medium in which the wave is traveling. So in this case, let's say we've got air on top and we've got water on the bottom. So air's up here, water down below at that interface. It turns out that light slows down in every medium besides the vacuum and air. We're going to cheat that one just a little bit. This slowing down causes the direction of the wave to change. So refraction is the changing of the direction of a light wave when it passes into a different material. You've experienced this when, like, if you've ever taken, I'm going to guess most of you don't put pencils in your teacups, right? Okay, but you might have seen this with a spoon. If you've ever sat on the edge of a pool, like you're sitting on the edge, but your legs are dangling in the water, and you notice that your legs either look broken or bent, or maybe your legs look sort of like short munchkin legs. If you've ever talked to somebody who's treading water in the pool, their head's above water, and you're talking to them, their body looks all, clown-shaped or whatever, okay? That's all refraction. It's coming about because the light that is coming from underneath the water, coming through that surface, speeds up, and as it speeds up, it changes the direction that it's traveling. We'll draw some more pictures about that. But this concept and idea about refraction comes down to the different speeds that these light waves are traveling. When I was teaching you about Maxwell's equations, I had you calculate the speed of light. Do you remember that? We calculated this number out, and it turned out to be like really close to 3 times 10 to the 8 meters per second. These constants that we talked about, this mu naught and this epsilon naught, those were the dead giveaways for electric and magnetic fields. That little naught, that little sub-zero that's sitting on there, indicates that those are the values in vacuum. It turns out that electric and magnetic fields get affected when they go into materials. They respond differently depending on the materials. In metals, especially iron metals, they respond very strongly. In other materials, they do the opposite. But we we don't do it this way, but we could go and try to measure mu and epsilon for a different material. We wouldn't put the sub-zero on there because it's not a vacuum. But we don't do this, okay? Because it turns out measuring those constants is pretty difficult. And instead in optics, we've got an alternative way that we will go after this speed, and it's called the index of refraction. We're going to use the little n because, well, we've never used little n before, right? No, we like to use it all the time as a counting number, don't we? And by definition, it's the speed of light in a vacuum divided by the speed that wave is traveling in the material. We'll learn a little bit later here today how to actually go and measure this index of refraction. But it turns out it's easier to measure the index and then figure out the speed of light in the material than it is to do it the other way around. Index of refraction is like a common, there's like agreed upon averages for many materials. I've managed to kind of memorize these because I just have used them so often in my career, both in graduate school when I was doing optics and just all through the teaching. You don't have to memorize them. I will give you tables or I'll give you information about index of refraction if you need it on your exams, that kind of stuff. But like, just to give you some ideas of the ranges of these values. Oh, what are the units? What are the units of the speed of light? See? Meters per second. And what are the units for velocity? Meters per second. So what are the units for the index of refraction? Right? It's a unitless number. Right? So that's why you won't see me put any units on it. So 1.33, and this is repeating for water. What does it mean? Well, we can go and we can solve for, I'll do it over here. if we take that index of refraction and instead we solve for the speed, right? We say, okay, do some cross multiplication, that kind of stuff, right? We can get this statement right here. So for water, right, if I calculate the speed of light in water, it's going to be the speed of light in vacuum divided by 1.33. All right, all the way back to 4th grade. Let's see, what 1.33 is that 4/3? Did I do that right? So that's C over 4/3. And what happens when you get a fraction in the denominator? It like flips over, doesn't it? So the speed of light in water turns out to be 75% or 3/4 the speed that light has in a vacuum. In other words, it's slowed down. And this is true for every material. The speed of light in a vacuum is the fastest light will ever go. Any other material will cause that speed to be lower. Again, just because of how the electric and magnetic fields interact with the materials. Index of refraction for glass. This is a bit of an average because different kinds of glass actually have different indices of refraction. You don't need to worry about that. But like 1.52 for flint, what we call flint glass or normal standard silicate glass. Let's see, if we do that one, we can get speed of light divided by like 1.5. I'll just round it. 1.5 is that 3/2, right? So that's C over 3. So this turns out to be 2/3. The speed of light, again, a slowdown. This is one that always sticks in my brain for reasons we'll talk about later. Diamond, that says diamond, is we'll call it 2.5. It's like 2.47. So that one's got a pretty big index of refraction. What are you noticing about the speed of light in the material as the index gets bigger? It's slowing down, isn't it? It's like the bigger the index of refraction gets, the slower, right, these waves are in the material. So for diamond, 2.5. Is that, that's 5/2? Is that right? So that ends up to be 2/5 the speed of light. The index of refraction of air, this is the other one that we will use all the time. We just call it 1. Now, technically, and I can never get the number of zeros correct, 1.0001, I think. In other words, air is pretty much what? It is pretty much vacuum, right? Like for our purposes, I mean, we usually only ever do 3 sig figs anyway, and we're within 3 sig. It doesn't matter that much. If you're actually measuring the index of air, you're doing something that's really critical in air, then you got to know it. But otherwise, we're not going to worry about it too much. Okay, so index of refraction is going to be the way that we're going to keep track of how fast light is moving in a material. And again, this matters because the amount of bend for that second ray, the refracted ray that ends up here in the water in my example, completely depends on what the index of refraction of that water is. It's all governed by a law called Snell's law. Snell, S-N-E-L-L. That guy was never made fun of in kindergarten, was he? Right? Right, yeah. This relationship right here, okay, you'll notice has the index of refraction of both materials, right? So N1, we always call, and I'll show you this right here, okay? Take a look at this, right? These are from a textbook. I don't think it's yours. So notice, right? See how the light rays coming from this flashlight and then it enters into the water, right? And they're calling that the incident ray, the one that is hitting or incident on the material interface right here. They called that side number 1. And then where the refraction happens, okay, is on side number 2 right there, okay? But look at this one over here on the right. Here they put the flashlight down in the water. We've changed which side is incident, right? The light is traveling in something, strikes a change in medium. Okay, so now our incident ray is on the bottom, and look what they've done with their notation. Where is number 1 ended up now? It's ended up down below, right? So don't get hung up on this. Don't ever think that like 1 is always the top and 2 is always the bottom. It completely depends on which way the light is initially hitting the change in medium. And I'll kind of demonstrate some of that too. Let me show you a video of refraction in action. I didn't mean for that to alliterate, but it did.
The beam is both refracted and reflected at the surface.
Bounce,
This
refraction.
is the reflected beam, and this is the refracted
I just said that.
Notice how the angle of each beam changes as the block is rotated.
And what can you say about the beam up there and the beam down here? Yeah, they look parallel, don't they? So the same amount of bend going in equaled the same amount of bend going out, right? It's just sort of a reversal of what was going on right there. Let's do this, okay? Let's do some what ifs. Okay, so if we have this air to water, right? Do you notice how I drew it? Right? Which one of these two angles is bigger? Theta 1 or theta 2? Theta 1's bigger. It's further away from the dotted line, right? It's further away from the normal. You can do this if you want. I don't recommend that you do it. You can actually go in here and play around with Snell's law to see what's going on with these angles. When you are going from, this is how I like to kind of write it. When you go from a lower index of refraction to a higher index of refraction, so n low to n high, it actually doesn't matter what the actual indices of refraction are. What matters is, are you going from a value that's smaller to a value that's bigger, or vice versa? So overall with Snell's law, when you go from a lower, like air, into water, which is higher, then your angle of refraction is always going to be smaller than the angle of incidence. So let's say our angle of incidence was 45 degrees. What are we guaranteed to have happen? What do we know theta 2 is going to be? Smaller than 45 degrees, right? So if in your calculations you end up with something bigger, you know something's wrong. Okay? It's got to be smaller. Now, the reverse is true. So if I come down here and I draw a picture, say, where we've got the beam traveling in water. We'll stick water down here. We'll keep that consistent, and we'll say that it's air up here. Now we are going from water to air. Well, which of those has a higher index of refraction? The water. So now we're going from a high index to a low index, and when that happens, our angle gets bigger. So theta 1, again, would be down low because that's our incident side. Theta 2, the refracted ray, would be up there in the air. And theta 2, in this case, is always going to be bigger than theta 1. The rule is that if you go from low to high, the light will bend closer to the normal. It'll get more vertical. And when we're going from high to low, it bends away. And this is going to produce some interesting optical phenomenon that we're going to be able to apply to real life here in just a second. Does anybody have, I brought my, can I borrow, Leona, can I borrow your plastic? Thank you. I promise not to drink anything and you'll get it back. Okay. What is the color of the water? Kind of a trick question, right? It has no color, right? Water doesn't have a color. It's what we call transparent, okay? What's the color of the plastic bottle that's holding it?
Less transparent.
Less transparent. It's just as transparent, actually. Okay. However, there are some cues that you are getting about the existence of the water and the existence of the plastic. What's telling your brain that something is there? Okay, so there's reflections, right? So you're seeing these kind of white, bright highlights that are coming off of all the lights that are in this room. Okay, and that's just a straight reflection coming off the surface of the plastic bottle. Okay, and a little bit of reflection coming off the water inside. But there's another cue that your brain is trying to grapple with, right? When it comes to what's going on here. What's the thing? What does our brain always assume about light? The light rays that are coming into your eyes, how did they travel to you? Straight lines, right? Anything that causes that straight line to deviate, your brain's going to start making up stuff like virtual images in the mirror and things like that, right? So the light that's passing into the plastic and then passing into the water, not only are you getting reflections, but you're also getting refractions. You're getting this bend, and your brain is like, wait a second, the light did something weird there. And it doesn't quite know. It follows the line straight back, giving rise to like my hand looks really big or something as I look through the water bottle. Weird optical illusions begin to crop up because your brain's trying to figure out where all these straight line rays came from when in fact they're not straight. But it's a cue to your brain that something is there. There's a material there that's different, right? And it's getting into the way. Everybody will notice that Leonella's going to get her water bottle back unmolested, except it's been part of a physics demonstration. Okay. Our brains can see transparent objects, even though technically we shouldn't be able to. Let's take a look at these windows right here, right? Okay. So how can you tell that there's glass there? Well, somebody's put a sign on the glass. That's like a dead giveaway, right? Okay, so ignore that, right? Okay, like look at the door here. Look up there. What's the clue that there's glass there?
Might be tinted glass.
It might be tinted glass, so the color's a little bit off, right? Obviously, Mr. Balogh, there's glass there because door, right? And there's a frame, right? That's holding the glass. Like there's all these cues that based on your experience, you know that glass is there. All right, I don't need a show of hands. This is a question for you to answer internally, okay? But how many of us have had the unfortunate experience where we walked straight into a sliding glass door being convinced that the door was open? This typically happens when you're carrying a tray of food or drinks for the party, right? And there's maximum social collateral, right, for the mess that ensues. What happened there? What was it that was gone that caused your brain to basically say, oh yeah, no, the door's open, go for it? Reflections are the first cue, okay? So it was probably in a situation, I'm going to guess, you're coming from a darker inside to a brighter outside, which means all the reflections would be on the other side of the glass, okay? Right? You're probably coming from an area that's not well lit, and so there aren't very many light sources, going to an area that is well lit, and so the reflection cues are gone. Also, somebody probably cleaned the sliding glass door prior to the party so that it looked like you and your roommates aren't slobs, right? Okay. And all of the smudges that are there, which is the other sort of giveaway that there's something there, right? Those were gone. So there's no reflection cues whatsoever. The other problem is that you were probably, like any normal person, walking towards the door straight, right? You're going to go straight through the opening. People don't normally say, oh, you know, that's a door, I'm going to come at it at an angle, right? You're probably coming at it nice and straight. Now that I've cleverly taken it off the screen, what does Snell's law tell us about these angles? If if I'm coming straight at the door, okay, the window is like, flat like this, and I'm coming straight at the door, what's my optical angle that I'm arriving at? It's 0, isn't it? I'm dead on, perpendicular to the surface of that glass. What's the sign of 0? 0. It's 0 or 1. You get a 50-50 chance, right? It's 0. So what's the refracted angle going to be? If one side's 0, the other side's going to be. So when light or you or anything else is incident at 90 degrees to the plane of the glass, there's no refraction cues either. So in the case of the party and the sliding glass door, there's no reflection, there's no refraction. So your brain says, open door, go for it. Index of refraction is vital to our perception of transparent objects. Check this out.
When we look at a transparent object, such as this glass eyedropper, we can see it even though it is perfectly clear. Differences in the refraction indexes of the glass and air allow us to see the edges of the glass. When we put the eyedropper in a liquid that has the same index of refraction as the glass and fill the dropper with the liquid, the eyedropper nearly disappears.
Where'd it go? What did your brain do? It erased it. You probably saw the very faint outline of where it was, right? Because they didn't it's hard to get like a perfect, right, index of refraction between the liquid and the water. But you could see it before because there was air in the dropper. There was a change in the index of refraction. But with no change in the index of refraction, there was no clue, no cue that there was any difference. And so your brain just kind of goes, whatever. There's nothing there. Why would there be anything there? There's nothing there to tell me that anything's there. All right, let's do an example of working with Snell's law. Snell's law. I mean, in terms of complexity, like mathematically, what's it looking like compared to the stuff we've done so far? Not too bad? If you know how to use the sign button on your calculator, you got this thing, right? Okay. The way that physics teachers decide to make optics difficult is to make problems difficult by setting up weird scenarios. So Snell's law is easy, okay? Snell's law is not a problem. But you'll know I picked this problem very deliberately from a textbook because I think it really outlines where the difficulty in optics is going to come from, okay? This problem is deliberately trying to trick you into making mistakes with something that actually is pretty straightforward. Snell's law is pretty straightforward. So let me see if I can't help you understand why this problem has been made more difficult than it really needs to be. I did not write this problem. I would never have written a problem like this. First of all, who has a cylindrical swimming pool? I mean, seriously. Mythbusters? Okay, sure. Why not? Right?
I guess they cut the tank.
The tank, right, whatever, okay. And then the tank is filled with water, right? Okay, so there's water all the way up to the top of the tank. I'm not going to draw the inside of the tank because I need the inside of the tank. They've told us that the tank's diameter is 3 meters. So I'm visualizing, right? I'm just trying to get a picture down, things that they've given me, all that kind of stuff. What do they want me to find?
How deep is it?
Yeah, the depth of the tank, right? I'm going to draw that depth, the thing that I'm looking for. In physics, we spell depth with an H. It's the height of the water column. So we're looking for how deep this tank is, right? But we've got to do it with some sunshine. And there's a couple of things that they've done that they don't really need to do. And I kind of warned you about this one already, right? 28 degrees above the horizon. What's the horizon? It's the horizontal, isn't it? Right? So they've given us this angle right here. Yeah, that's not the angle we need, right? No. Okay? So there's the first trick. Right? Like they're just trying to screw you up, right? There's no reason to do that. It really isn't. Okay? They could have just has said, is that 62 degrees? Yeah. From the vertical, right? They could have just given, there's no, again, don't know why they do this. The second part of this is that they're being cagey. They didn't give a picture, okay? They're being cagey about how you're going to figure out, right, where the light hits on the surface of this tank. The clue is that the sunlight does not illuminate the bottom of the tank. What is the absence of light called? Darkness. What is the absence of sunlight called? Your shadow, right? So basically, what they're trying to say is that the shadow of like the walls of the tank is such that the bottom of the tank is in shadow. And they didn't really say that, right? Sunlight ceases to illuminate any... Why? Just say the bottom is in shadow, right? So the only way that that could possibly happen, right? Since light does travel in straight lines as long as it's in the same medium, the only way for that to happen is for light to have like entered up here and traveled down till it hits over here. And there, in other words, there's no light down here. It could have come from the other direction too, right? But the point is that like, let's say light strikes the surface here and refracts, right? Or like over here and refracts, right? Really, it has to hit here and refract, right, in order for there to be casting a shadow. Because if it comes in like this and refracts, then this part's in shadow, but this part isn't, right? And if it came from straight down, it would always be illuminating. As the sun goes across the sky, right, you get these situations where the light comes in like this, right? So really, it's only at these extreme points where it's hitting the edge of the tank that you're going to get a situation where this is all going to be in shadow. And so what I'm going to do, and again, how are you supposed to know this kind of stuff, right? Like, why, just tell me. Sunlight enters the edge of the tank. Okay, so the sunlight comes in, and I'm going to put the correct angle of 62 degrees from the vertical. So sunlight's coming in like that. Are we going low to high or high to low? We're going from air to water. Low to high. It's a low to high, right? So we know that the angle, the refracted angle, is going to be less than 62 degrees. So this angle right here, theta 2, is going to be less than 62 degrees. So we're going to have that situation like that, okay? All of the area above the sunbeam is going to be in sunlight because I can get other, like it's hitting other portions of the surface as it comes in and bending in, so that's going to all be there. But this beam is the last one, because any light that comes here just hits the edge and then there's nothing, right? So this is the last beam at this angle that's going to hit this edge of the tank. And what we're looking for is like that condition, right? 62 degrees is going to help us figure out what the depth of the tank. Have you noticed like all of the mental gymnastics we've had to do just to try and set up the problem? We haven't even used Snell's law yet, right? And all of this garbage has been piled on top. This is what I said, that like physics teachers just go out of their way to make optics problems harder when they don't need to be. Okay, well, how is theta 2 going to help us find h? Well, yeah, we can get theta 2 from Snell's law. That's not a problem. I'm still trying to map out what the heck I'm doing here, right? So if I have this angle, and I have this side is 3, and this side is h, how do I find h? It's the trig function nobody ever wants to think about. Tangent, right? Tangent is SOHCAHTOA. Tangent is opposite over adjacent. What's the opposite side here? 3. What's the adjacent side? h. So I'll be able to find the depth of this tank if I take 3 and divide it by the tangent of my angle that's up there, which is theta 2. We're going to find theta 2 by applying Snell's law. So now we roll. Okay? N1 is 1. That should be a sine theta 1 right there. I got overly excited. Luckily, Dean McManus had left. She didn't get to see that mistake. She's a biologist by profession, so she probably left because I either did a really bad job or it was physics. One of the two. Sine. What's our first angle? 62 degrees. N2 is water, 1.33. Sine theta 2. All right, I got to solve for sine theta 2. How do we solve for that angle if it's trapped inside of a sine function? Yeah, we got to take the inverse sine, right? So divide both sides by 1.33, and then this whole thing, I'm going to take the sine inverse of. I don't have this one in my notes for some reason. Somebody's going to have to tell me what this angle is. It's the inverse sine of the sine of 62 divided by 1.33. Did I beat you, or did somebody get it before me?
41.6.
So 42? 42 is a good number. Okay. So now I know what that angle is. And so the height's going to be 3 divided by the tangent of 42. Tangent of that number divided by 3. I got 3.4. Right? Like I said, the Snell's law part, not hard. It really isn't. If you know how to hit the inverse sine button on your calculator, you're home free. It's kind of the rest of these problems sometimes. They get really kind of weird, right? So don't hesitate to hit the tutorial center, email me, like, Mr. Balogh, I don't understand what this question is. And I'll be like, oh, it's being stupid here. Just do this. Right? It doesn't really need to be that difficult. Let's do a quiz. It's been what have we done? 4 chapters that we haven't done a quiz? So that's the law of refraction. It's Snell's law. We're going to start applying it to various situations that you encounter, well, some of these on an everyday basis. The first one we want to tackle is something called total internal reflection. Bad name, because this is actually refraction taking place. Let me show you what's going on here. Material, interface, right? We have, doesn't matter what the numbers are, all that matters is that we go from a high to a low index material. In other words, the light's traveling in the high index, strikes the surface, and gets refracted. The angle, what's the angle going to be? Bigger, has to be bigger. We're going from high to low. How big can that refracted angle get? Remember, we measure all angles from the normal. So what's the largest angle of refraction we could possibly have?
Twice. Bigger.
So if theta 1's 45, we know it's going to be bigger than 45, right? So could it be 50? 80? 90? 110? What does an angle of 90 degrees look like? Perfectly horizontal with the surface, right? In other words, if the angle becomes 90 degrees, if the refracted angle becomes 90 degrees, technically the light has not left the material. It's traveling in the surface of the material, but it has not exited out of the material. And any angle above a very special angle called the critical angle. I'm going to change this angle symbol right here, okay, theta sub c. Any additional angle above theta c means that the light will be completely reflected in the material. It's called total internal reflection, because what we've done is we've gotten to a situation where the refraction is bigger than 90 degrees. In other words, no refraction takes place. No light exits the material. And I'm not speaking as a physicist, right? And you know, physicists sometimes like, oh, there's no air friction, just wink, wink, right? There's no air friction, ignore it, right? No, no, no. This is not just some like, we're getting close to it, but it's not exact. It is exactly zero transmission into the other material. When you hit the critical angle, or you're bigger than the critical angle, the light is going to stay inside of the incident material. You lose none of it. It stays reflected. To calculate what this critical angle is, we use Snell's law. I'm going to change the subscripts just a little bit, because personally I get confused with 1 and 2 too often. So I'm going to change this. I'm going to go n high sine theta critical, right? Because we're in a higher index material and we know we're at the critical angle. There's a lower index of material, and then the angle in the lower index is 90 degrees. Again, we're solving for the angle where the refracted ray is going to go to 90. Anything bigger than the critical angle is just going to be no refraction. Anything less than the critical angle will have Snell's law. We could go calculate it. But anything above this, and this light is going to stay entirely inside the material. Well, what's the sine of 90?
1.
Solving for the critical angle, I'll get n low over n high, just multiply or divide both sides by n high, and then the critical angle is going to be the inverse sine of the lower index material divided by the higher index material. In your book, they will write this as inverse sine of n2 over n1, I think is what they'll do. And then you can get messed up as to, well, which one's 1 and which one's 2. The reason I write it like this has to do with the sine function and the geometry of optics. Let me see if I can't explain. Let's do a what if. What if we were in water and we're going into air? Okay? We start in water, we're going into air. What is n high? 1.33, right? What's n low? 1. How did you do that?
Just by looking at the answer.
1 is less than 1.33, right? And it doesn't matter which one's 1 and which one's 2 or anything like that, because of the following. If I calculate this critical angle, get your calculator out, somebody tell me what this is. The low is 1 and the high is 1.33. What is this angle? It's going to be like close to 49 degrees.
48.7.
48.7, so we'll just round it to 49 degrees, okay? What happens, everybody try this so you know what your calculator does. Try sine inverse of 1.33 over 1. Let's just say you flipped it, right, by accident. What's the inverse sine of 1.33?
Domain error.
Domain error? Well, that's a useful. Did somebody else's calculator say something different? What's it say? Domain error? Error? What the heck you trying to do? Did anybody get that error? No? Okay. What's happening here? What is the inverse sine function asking? You take the inverse sine of a number. The question is, what angle will give a value for sine that is this number? And we just asked it, what angle does sine of that angle equal 1.33? What's the answer to that question?
Never happened.
It never, because sine can never be what? Bigger than 1 or negative 1, right? Sine, the cosine and cosine, they live between values of 1 and negative 1. And so when we go and ask the question, what angle gives a value for sine that is 1.33, it goes, what are you smoking? Can't do that, right? I like to think of total internal reflection as an interaction between higher and lower index materials, which is why I write it like this. You can never get this to happen if the light is traveling in a lower and going to a higher. This will not happen. But if light is in a higher index material and tries to go into a lower index material, it's possible. What is the angle where that's possible? Well, it's the critical angle, right? And I can always get the critical angle if I keep track of my ratio has to be less than 1, right? And so that's got to be low divided by high. And now I don't have to worry about which one's theta 1 and which one's theta 2. I can nail the critical angle every single time. Why are we talking about this critical angle? What?
So that's telling me any angle less.
Yeah, so let's take a look at this, okay? So here's our ray, okay? And here's the incident angle, right? We know that on refraction, theta 2 is going to be bigger because we're going from high to low, okay? There is going to be a reflected portion, right? But the refraction is what we're looking at. At the critical angle, this critical angle right here, which in the case of water is almost 50 degrees, the refracted ray will be 90 degrees, right? As we get closer and closer to the critical angle, these get lower and lower and lower. Like theta 2 always wins in this case. Theta 2 is always bigger than theta 1. So theta 2 is going to reach 90 degrees before theta 1 does. And we call that spot the critical angle. And anything after the critical angle guarantees it'll just get reflected. Sorry, I drew those wrong. It'll get reflected into the material. Nothing will leave the surface. And that nothing is like nothing leaves the surface. It's not like we're faking it, right? And winking and that kind of stuff. I'll prove it to you. Maybe. Where'd it go? Right there.
We'll use this water tank and a parallel beam of light to demonstrate total internal reflection. A chemical in the water fluoresces when the light strikes it, showing the path of the beam. This mirror reflects the beam up to the surface of the water at any angle we choose. When the beam strikes the surface straight on, very little of the light is reflected. At a shallower angle, more of the light is reflected, but most still passes out into the air, as shown by this thread screen. Notice the misalignment between the beam in water and the beam in air.
Due to refraction.
At a still shallower angle, the beam is refracted so much that it becomes parallel to the surface.
That's not a parallel line.
This is known as the critical angle situation. If the beam hits the surface at an angle shallower than the critical angle, all the light is reflected back at the surface, and none crosses through.
There's nothing on that thread screen.
As total internal reflection.
It stays inside of the water and nothing comes out. Okay? So in high school, I was a swimmer. I was on the swim team. And this is a picture. This is what it used to look like when you were at the bottom of the pool kind of looking up at the surface. Okay? it looked black because our coaches were so mean to us. They deprived us of all oxygen. And no, sorry, I just didn't push the button. Okay. So this is what it would look like. Now, on this particular pool, they've removed the lane lines, the plastic things that you don't run into. Swimmers are dumb, or we're really stupid. We need to follow a line on the bottom of the pool, otherwise we run into each other, right? So you spend your entire practice just following a black line on the bottom of the pool, right? So they've taken the plastic lane lines off, the ones that float at the surface, and so that we can see this effect. Now, we're down here at the bottom of the pool, we're looking up, and do you see that, like, I don't know, black halo up there, right? So this is an indoor pool where this picture was taken, and you can see the lights that are on the ceiling of the pool, those bright lights that are up there. So when you're in the water and you're kind of looking up, you see out of the water to a certain angle. What angle? We just calculated it? The critical angle, 49 degrees. So 49 degrees to the left, 49 degrees to the right, 49 degrees in front, 49 degrees in back. Basically about 100-degree field of view where we can see through the surface of the water. Everything past that is a reflection of what's already in the pool. So you see how the bottom surface, the real concrete of the pool, is reflected into the surface of the water up there, right? You see total internal reflection up to the point where we're past that critical angle, or at least smaller than the critical angle, and then we can see what's above the surface. This is a scuba diver photobombing another scuba diver's shot, right? But again, trying to show the same effect here. Now, here this camera is struggling with the dynamic range. The ocean is typically not dark like this, okay, unless it's nighttime. But the camera is looking at a very bright, blue sky, and it's having trouble showing us what's going on in the rest of the water. But this ring that you see, and I used to scuba dive, you go down and you look up, and sure enough, you'd see the sky, but only in this narrow field of view. About 50 degrees that way, 50 degrees that way, you could see the blue sky. Otherwise, all you saw was a reflection of what was going on underneath the water in all directions. It gets a little bit disorienting sometimes because you look up and you can't see the sky. What you see is a reflection of the bottom, and you're also neutrally buoyant, so you don't know which way gravity is pointing. And you can very easily sort of get flipped over in terms of like which way is up, which way is down. You start swimming for what you think is the surface, and you bonk your head on the floor of the ocean, right? So it can be a little bit dangerous, but you learn how to deal with that. Okay. This is kind of fun.
These acrylic tubes will be used to show the type of total internal reflection which makes fiber optics communications possible. When a laser beam is aimed into the end of this tube, the beam bounces off the walls and is guided along the length of the tube, emerging from the far end. The laser beam can also be guided along this curved tube. Real fiber optics cables can bend around corners without losing any of the light passing along them.
So that laser is completely inside of that piece of acrylic plastic, right? So what's a fiber optic? Have you heard of fiber optics? What do fiber optics supposedly do?
Internet?
Yeah, they do internets, right? I'm going to guess that at some point today you've used the internet. Even if you have just thrown your phone into the deepest, darkest part of the ocean, your life today has been determined in part by the internet and what's going on it. Internet communications are made possible in our modern day and age by high bandwidth connections between things. Bandwidth, I don't want to get too far off the rails here. Bandwidth is a bit of a lie. It's not the right word to use. but it's kind of like how fast information can travel on wires or fiber optics. The bigger your bandwidth, the more information per time that you can send. So let me do a what if. I'm going to guess that a lot of you are probably using, like, if you're not just solely on your like cell phone's plan for your internet, you might live at a place that's got like wired internet and then it goes into like a wireless, like Xfinity or something like that, right? So if you've got like a wired to the place where you live and then it turns into Wi-Fi, right? We can say that like the amount of bandwidth available to where you live, that's not your cell phone, is maybe represented by this pencil. Like this is, think of this as a pipe, right? A pipe of this size, and you can have a certain amount of water going down this pipe. There's like a maximum amount of water width that you can send down this pipe, right? Like gallons per minute can go down this pipe. Similarly, with internet, it's called bandwidth. It's a certain amount of information for the size of wire that you have. It's not actual physical size. It has more to do with the materials inside the wire. Fiber optics, even the most basic fiber optics, would be a pipe. The equivalent scale here, if this is a copper wire at like say 1 gigabit per second, a fiber optic could carry a pipe that would be the size of a 6-foot tall sewer pipe, 6-foot diameter sewer pipe, right? I'm 5'5", so maybe a little bit up here, right? Imagine a pipe this big around, and that's the amount of bandwidth that a single fiber optic can carry, right? So fiber optics can carry a lot more information. They're just a bigger pipe. The way they do that is by taking advantage of total internal reflection. A fiber optic consists of optical glass. It's a glass fiber that has this coating or cladding around the outside. The manufacturer, usually Corning glass, will create the glass fiber, and this is like ultra pure glass. Like we're talking, there's only 1 atom's worth of impurity, like for every 2 or 3 meters of fiber. Like over about 10 feet, you'll have only 1 atom that is out of place. This stuff is incredible in terms of its purity. They need it that pure because any impurities will cause the light to bounce off and get scattered and lose its energy. So they make this glass core. They put a cladding around the outside that has to have an index that is higher or lower than the glass. We want the light to stay completely inside the fiber optic. Lower. The glass is high, the cladding is low. Make sure that laser beam always enters the fiber optic such that as the light travels, it's guaranteed to hit either at the critical angle or more. So like try to send it in as straight as you can. And therefore, every bounce against the wall of that fiber optic cable will guarantee the light stays inside of the fiber optic. We call it an optical pipe or a waveguide. It keeps the light inside. Now, copper wires like Ethernet cables and coaxial cables, you can go about 75 meters or about 150 feet before you have to boost the signal again. There's enough signal degradation in copper wire that you need to have a router or switch or something in place in order to take that signal and go, okay, we're gonna repeat that signal, we're gonna amplify it and make it bigger again. Fiber optics can go kilometers, like several miles between repeating stations. Okay? There's some fiber optics that can do it all the way across the ocean with very few repeating stations. It's actually quite incredible, and it's enabled like global communication in a way that is really quite difficult to get into your head. So here's an old man story for you. When I was living in the Philippines as a missionary, the first year that I was there, the only way that I could talk to my family on the phone was through satellite communication. So my local phone company, I'd have to call them up and say I need to make a phone call to the United States, and they would have to call me back after they had routed the call through some satellite to my parents' house, right? And so the operator would call me and say, okay, your call's going through now. I'd pick it up and I'd say something, and like 3 or 4 seconds would go by before I heard the reply. There was this time that it took for the signal to travel up to the satellite, for the satellite to process it and to send it down, and then for my parents to reverse that, right? And so we'd end up talking over each other, or it'd be like talking on a radio, like 10-4, do you hear me? Is it clear? Okay, wait for, it just took time. It was kind of awkward. At least you got to talk to them, right? In the second year I was there, the first fiber optic communication lines had been laid between the Philippines and, in this case, mainland China, which then went to the United States. But I got a call through on a fiber optic line, and I didn't know it. I thought it was going to be like the satellite again. It was like my family was in the room with me. We carried on a normal conversation with all of that, talking over each other and having fun and all that kind of stuff that we normally would. And I basically just cried for 30 minutes on the telephone call, right? Because before there was this separation, like temporal separation, not just physical, but like you couldn't talk to them on the phone normally, right? And then all of a sudden, fiber optic communication, not only is the distance much shorter, right? Which they're both traveling at the speed of light, but the fiber optic connection was clear, so there was no hiss or static, and it was fast. It was quite incredible. And ever since, like, you pick up your phone, you can call anywhere in the world. And it's like the person is just right next to you, right? Do it with FaceTime or Zoom or anything else, right? The world is a big place, but it has gotten really small when it comes to our communications. And it's in part because of fiber optics. So, the internet, brought to you by Total Internal Reflection. All right. Let's do this, okay? We talked about polarization a little bit. I just want to do this one kind of in passing. At certain angles, one angle in particular, called the Brewster angle, light can get reflected and become completely polarized in the horizontal. The reason it's never vertical is because electrons, which are responsible for absorbing light and re-emitting it from a surface, electrons can't wiggle up and down out of the plane of the surface. They can only wiggle in the plane of the surface. So at a certain angle, unpolarized light can come in, get reflected, and be completely horizontally polarized. Horizontal in the same plane as the surface. That angle where that happens is called the Brewster angle. And it's found, I'll do it the way your book does it. Okay, actually I'm not going to do it the way your book does it. I'm going to do it my way, because they used N2 over N1 again. Okay, but this one is always N high divided by N low. You're going from usually air into some material that's not air. Sunglasses, I mentioned this last time. Which way would you put the polarizers in sunglasses to knock out this horizontally polarized light? You want to put them vertical, right? So in sunglasses, the polarizers are always mounted vertical to cut that horizontal glare. The equation for finding the Brewster's angle is the inverse tangent of the ratio high to low. The light's traveling in this lower index of material, usually sunlight and air, and then tries to refract into the other material, bounces off. This typically happens with highly reflective surfaces, so metals and glass, like not so much with an opaque surface like this one. But again, I think maybe I gave you a problem where you've got to calculate the Brewster angle. So there's the equation. That was just kind of a side light. Let's instead talk about one of the most beautiful results of optics and index of refraction and the changes in the speed of light as they go into materials. I say most beautiful because this particular idea, dispersion, is responsible for some of the most beautiful natural phenomenon that we get to experience. Dispersion, simply put, is an idea. It's a statement of fact. The index of refraction is different for different colors of light. We talk about the color of light as its frequency and or its wavelength. In optical physics, wavelength and frequencies are just yin-yang of each other. We've talked about this before, right? Short wavelength is high frequency. Long wavelength is low frequency. So they're opposites of each other. High frequency, short wavelength light is blue light. Red light is the opposite. It's got long wavelength, low frequencies. It turns out that the index of refraction does not stay constant for any of these different colors of light. Don't panic. I'm not going to require you to read a dispersion chart. Okay? I'm going to give you the index of refraction for whatever color light we're using. Don't worry that, if it says red light, you can just go ahead and use the index for glass, which is 1.5. It's kind of an average. But I do want you to kind of appreciate, do you notice here how, and the colors are across the top, right? The blues, indigos, and violets over here, right? They have higher index of refraction, don't they? These curves for all these different materials, right, come down and get lower as you move more to the red side. Because Snell's law gives us the angle of refraction, and that depends on the index of refraction, when white light enters a material, it will spread out into its component colors. Every color has its own angle that it will refract at. And we call this spreading out of the colors, because the index of refraction is different for different frequencies, we call that dispersion. So a prism disperses the colors in white light. If you handed a kid a piece of paper and a box of crayons and told them to draw a picture of the sun, or draw a picture with the sun in it, what color would they reach for to draw the sun? Orange, brown, that's Fresno speaking, right? Okay. Normally yellow, right? But what is the actual color of the sun?
White.
It's white. Okay, you leave the Earth's atmosphere, you go into space, the sun is white. Okay? So why does the sun appear yellow to us, or brown to us down here? Most of one color has been taken out. Which color has been taken out? Blue. Where'd the blue go? Right? Okay. We're going to answer why the sky is blue later. It's not because of dispersion. Okay. It's something else called Rayleigh scatter. We'll get there later. Okay. But the sun appears yellow to us because most of the blue has been taken out, right? But white light is the combination of all the frequencies, all the colors of the rainbow put together. When you shine white light on a prism, the different indices of refraction cause a spreading out of the different colors, and you'll get that telltale rainbow, the Roy G. Biv of white light. And I called this the most beautiful because, in fact, you can get these rainbows without prisms. You can get them from water. What am I literally talking about? Rainbows. Before there was the guy on YouTube that got hundreds of millions of views for freaking out over a rainbow, there was me. Right? It's too late for me. Right? Should have recorded my shenanigans in class before then, right? But let's talk about rainbows, where they come from, and hopefully increase the magic for you. I've been accused by others that don't understand, right? You're a scientist. You make everything beautiful boring. I disagree. I can almost guarantee that in a room full of 30 people, I understand in more detail than anybody else what causes the sun to rise in the morning. Like almost, unless there is a planetary physicist or an astrophysicist in the room, I'm your man for explaining how the sun rises. That does not take away the beauty or the wonder of watching a sunrise. I wake up very early in the morning. I'm driving to work while the sun is rising over the mountains. I come close to crashing every morning because I just see that light peeking over the edge of those mountains. And I'm transported. I'm gobsmacked. I'm like, it worked again. Like, it's complicated. But it works every day. And it's gorgeous. And it's beautiful. And I know where the colors come from. And I know when it's going to happen. And I can predict when it's going to happen tomorrow. And I know the time. I know it all. But that doesn't take away from the beauty. So I hope in this explanation, you're going to walk out of here appreciating rainbows. Maybe even more than you already do. A rainbow comes about because of a special alignment of the sun and the water droplets that are falling from a rain cloud. In this picture, you can kind of see it over here, right? This person has the sun behind them, behind and above, right? And we've got some bounces in the water droplet right there. We'll come back to that picture in just a second. The particular arrangement that you need in order to see a rainbow naturally in the sky is one where the sunlight is coming from behind you. So there's really only a couple of directions and a couple of times of day where you can see a natural rainbow, one that's created by a rainstorm in the sun. So why only a couple times a day in a couple of places? What happens over here with the sun? Sun rises over there, doesn't it? Okay. And what happens over there? Sun sets. Okay. So when the sun rises, where might you see a rainbow? The sun has to be coming from behind you, right? So to see a rainbow in the west, what time of day does it need to be? Morning. So that means you need to have rain falling somewhere to the west of you with sun coming over your shoulder from the east. Generally, mornings are the most stable times of day when it comes to air and thunderstorms and all that kind of stuff. Takes the energy of the sun to get things ramped up and for things to start happening in the atmosphere. So generally, you don't see morning rainbows. They're pretty rare compared to afternoon ones. But in the afternoon, as the sun is getting lower and lower and lower in the horizon in the west, if we've got rain, especially over the mountains, convective activity is lifting all of that moisture up and it's starting to fall out, right? You have a good chance, if there's no clouds over there, or at least the sun goes low enough to poke through the clouds, right, to shine on the raindrops, you'll see rainbows over in the east. What's going on, oops, wrong device. What's going on, okay, is light enters the top. We're going to model a spherical raindrop. This is actually pretty close to what the actual raindrop shape is. It's a little bit different, but overall it averages out to being spherical. Sunlight enters the top of the drop and begins to disperse. The different indexes of refraction of the different colors of light mean that they start spreading out from each other. They refract, reflect, they do some things. They take one bounce off the back of the raindrop. Again, there's reflection and refraction going on right there. In fact, there's a lot more refraction than there is reflection off the back side of the raindrop. A lot of light exits out the back of the raindrop. But some of it gets reflected off the back, hits the front surface, refracting yet again, dispersing even more. And so by the time the light exits the bottom of the raindrop, it's dispersed, it's spread out. You've got the Roy G. Biv phenomenon of the rainbow. So this is a picture that my father took many years ago, okay? And you can see here that he's taking a picture of a rainbow. Now, where's the sun? You can see the sun is touching the tops of the trees right there, right? But you see how the bottoms of the trees are in shadow? So this sun is like setting or going behind a cloud or something like that, right? You can see the sunlight's actually pretty orange, so it's got to be pretty low on the horizon. We'll talk later about where the sunset comes from. Later, as in chapter 27. So we've got the bow, right? And the sun's coming from behind. This picture has not been photoshopped in any way. In other words, he took it, he didn't take it in RAW, he took it as a JPEG, so the camera processed it a little bit. But this is as close to like what the camera was seeing that I can present to you, okay? So this is actually a pretty strong rainbow. Sometimes they can be a little fainter. It really depends on how much sunlight is coming over your shoulder, right? The curious thing is that rainbows always are exactly the same size when you're looking at them in the sky. Dispersion and Snell's law come together to give us a 2-degree difference between the red portion and the blue portion of the electromagnetic spectrum. 2 degrees separating the red portion of the sunlight from the blue portion of the sunlight, which means that a rainbow always takes up 2 degrees of your field of view. So it's always more or less the same size. Sometimes you get sections. I've seen rainbows where like you got the first side and then there's nothing and then it continues over here with another piece. That has everything to do with where the rain is falling, right? If you have rain here but nothing in the middle, you'll see portions of the rainbow, right? Maybe you only see one segment because the raindrops aren't consistent or they're not being illuminated by the sun evenly. So what time of day do you want to go rainbow hunting? Morning and evening, but usually in the evening, right? Nobody's, except Mr. Balogh, awake in the morning, right? And evening is when more people are awake and things are going on. It also needs to be raining, which means we're not probably going to see a rainbow around here until what? November, right? Okay, so yeah. If there's any thunderstorms this summer, go look for rainbows. Okay, so we know that rainbows are brought about because of a certain a situation where you need sunlight and raindrops being in opposite parts of the sky. You see a bow, an arc, that is always 2 degrees of your field of view in width. But there's more to it than that. You are standing at the center of an optical phenomenon. The rays of light that you are seeing are coming to your eyes as they have refracted and dispersed through raindrops. If you shift your point of view, the rainbow you see shifts so that you are always at the center of all of these angles and all of this geometry. Yeah. What's that? Yeah, we're going to talk about double rainbows. It's a good question. Let's handle the single ones first. We'll get to the doubles. This means, among other things, that every rainbow you've seen and every rainbow that you will see is your own personal rainbow. Nobody else can see the rainbow that you are seeing. It's true that a bunch of people can go, oh, look, a rainbow. But are they seeing that rainbow? No. They have their own set of sunlight, raindrops, and center of optical phenomenon. Every rainbow you've seen, every rainbow you will see, is your rainbow. A gift to you from the universe because you were at the right place at the right time for all of these things to line up. So enjoy it. It's yours and yours alone. Second, St. Patrick's Day is tomorrow. And as we know, all the leprechauns come out during St. Patrick's Day, right? Okay, some obscure holiday about Catholicism coming to Ireland way back when, right? But where do leprechauns keep their gold? At the end of a rainbow, right? Okay, right? Since you are at the center of this optical phenomenon, what happens if you try to step towards the rainbow? It moves. It must always take up 2 degrees of your field of view, right? Okay? Don't try this one at home, but if you've ever been driving and seen a rainbow, what does the rainbow do? It moves with you. It's following you. This means, among other things, that leprechauns are really smart. Because no matter how hard you try, you can't get to their pots of gold because the rainbow is always the same distance from you, right? But it gets better. The bow isn't a bow at all. It's a circle. We hardly ever see the circle because the ground gets in the way, right? But if you can get up high enough, you can actually see the entire circle. You're at the center of a phenomenon that has circular symmetry to it. In this particular picture, this was taken from an aircraft, and you can see that they've managed to capture most, right, of the circle, right? There's a little tiny bit down here that goes into shadow that doesn't quite make it, but very definitely this is a full circle. You can do this if you're on top of, say, a tall building. It's got to be fairly tall for you to be able, for the ground to get out of the way far enough. I have seen this in the mountains, being on the peak, like we're talking like 10, 13,000 feet above sea level in the Sierras, right? Where the sun, again, it's that time of day, and you have to be able to look down into a 4,000-foot drop to be able to see it, but I've seen it. I see it most often while I'm flying. I always pick my seat in the airplane. Number one, be a window seat. Number two, on the northern side of the plane. In the northern hemisphere, the sun is coming from the southern part of the sky. It's flipped when you fly on the other side of the globe, but I've never been to the southern hemisphere. So I make sure that the sun is on the opposite side of the plane from where I am sitting, depending on whether I'm flying east or west. Why? The sun's coming from over there, or maybe up above, right? But it's coming from over there, generally. And if I look out my window, I'm usually looking down on the tops of clouds. What are clouds made of? Water droplets. From a plane, you can almost always see a rainbow. And it's a circle with the shadow of the plane sitting in the middle of it. It's one of the things that makes flying an economy class bearable. Somebody asked about the double rainbow. Okay, where does the second one come from? This picture has been photoshopped. Okay, I got this from a textbook publisher a long time ago, 2006. Holy cow. But they have enhanced the rainbow colors in this one. Rainbows typically aren't this vibrant, and the secondary is usually very faint. It can vary a lot with the atmospheric conditions at the time. But the answer to your question, Tommy, where does the second one come from? The primary came from the sunlight entering the top of the raindrop. The second one comes from the sunlight entering the bottom of the raindrop. The secondary bow consists of light entering near the bottom. Of course, it's entering everywhere, right? But the stuff that enters the middle basically goes out the backside. Nothing ever happens. It's top and bottom that are interesting. In the bottom, in order to make it back to your eye, there has to be 2 reflections. On every reflection, you are losing approximately 80 to 90% of your light intensity. So it goes in, loses on that first reflection, it's like 80% down. And then on the second reflection, it's like 80% down from that 80% down that we started, right? Like it drops off really fast, which is why the secondary bow is pretty faint by the time that it gets to your eyes. Cameras struggle with this. You have to do a special kind of photography called HDR photography to really get the dynamic range of the different amounts of light that are coming in. This is, again, my father taking that picture as raw as we could get it from the camera. And you can see, can you see the second bow? It's like super duper faint. This is typically what it kind of looks like. You can easily miss the second bow, especially if the sun's like pretty bright in the sky. They're much easier to see when the sun is closer to the horizon and it's being attenuated a little bit. Okay, but it's there. It's sitting there. Okay, the first color order, the Roy G. Biv, is reversed from the secondary bow. In fact, the first primary bow is an inversion because you've had one reflection, and the one reflection inverts it. On two reflections, it inverts and then inverts it again to bring it back into the original orientation for the image. But the second rainbow does come from light entering the bottom of the raindrop. So your homework for the rest of your life is to chase rainbows. Because the rainbows you are looking at, those are your rainbows. Your gift from the universe for being present and having your head up and realizing, oh, it's raining and the sun's going down. I should be looking for rainbows. I'll see you tomorrow, where we will talk about and start doing lenses, applying Snell's law and the law of refraction, to the lenses in our eyes and the lenses on our faces. I am available till 2 o'clock, right? I'll just be here. If you want help on your homework or anything like that, you have any other questions, I will just be here. Otherwise, have a great rest of the day, and I will see you tomorrow.